Very good. I'm going to talk about materials challenges in low nuclear energy reaction. My name is Ashraf Imam. I'm from George Washington University, and I was part of Department of Defense at Navy at Naval Research Laboratory. I'm going to give you an outline of my talk. And basically, I'm going to talk about materials challenge. And there, this is the outline. So I will introduce the fundamental concepts in material science, then move on to material structure and composition, which is very important. And there I will discuss imperfections in solids, then go on to the strengthening mechanism, then talk about something about diffusion in solids, which relates to the kinetics of the reaction. Then how structure dictates properties, I will talk about that. And then how processing can change the structure. And then talk about materials related issues. Then go on to calorimetry, then progress, and then finally the summary of the talk. So let's take a look at it. What is materials challenge? We all know that materials has a lot of issues. Question is, why should we know about that? Materials drive our society. We all know that. We gone through a Stone Age, then went to the Bronze Age, then went to the Iron Age, and now question is now where we are now. Some says we are on Silicon Age, and some say no, we are on polymer age. But anyway, moving forward, what I'm trying to show here, that for any reaction, chemical or nuclear, we have a reactant and we have a activation energy. And what happens when proper conditions are met, we get a product and we get energy release. If it is a chemical, the energy release is roughly around 1 electron volt. If it is a nuclear, the energy is 10 to the power 6 eV, so it's much more gain there. And that's where we are going to talk about what is the proper condition to get to the nuclear energy. Moving forward, proper condition. It requires an interdisciplinary approach. So it's not like one discipline. We may have to deal with the physics, may have to deal with chemistry, may have to deal with nuclear physics, electrochemistry, solid state physics and chemistry, instrumentation, science and technology, and maybe possibly electrical, mechanical, and thermal engineering, statistics and data analysis. But what I'm going to talk about, I'm not going to talk about other things except the material science aspect of it. So moving forward, to make so dealing mainly with the limited materials issue. Again, in the material science is a big subject. So I'm going to deal with just limited issue which affects our low energy nuclear reaction. So if you want to make a selection of materials, what we need? We need, first of all, we pick up the material, what application it is needed, and then determine the properties, mechanical, electrical, thermal, and all those things. We look into that. Then we look into what properties we can achieve from that, identify the candidate materials, then find out what is structure and composition. And then finally, we identify the processing, and processing changes a structure and overall shape. And we are going to talk about casting, sintering, vapor deposition, doping. So some of those things I will discuss here. So one of the main feature of LENR experiment is that it depends on both the composition and the structure. But another interesting part of it, that the composition and structure may change during loading. So moving forward, then we are going to talk about basically now introduce the fundamental concept in material science. And again, it is a fairly large subject, so I don't envision to go into all the details. So looking at imperfection first. So imperfection, there is no such thing as a perfect crystal. What are these imperfections? Why are they important? And because many of the important properties of materials are due to the presence of imperfection. Defects may be desirable or undesirable. For example, dislocations may be good or bad, depending on whether plastic deformation is desirable or not. Now I'm going to talk about different types of defects. So you have defects of one dimension, which is what we call it zero dimension. One dimension is dislocation, zero dimension, and then 2 dimension and 3 dimension. And in 0 dimension, we have vacancies, interstitials, substitutional. Then one dimension is dislocation. Then we have defects, grain boundaries or interfaces. Then in 3 dimension, we have voids and cracks in occlusions. Moving forward, let's take about what are the different ways we can make the material stronger. Again, these are the fundamentals which I'm going to touch base with you, which may be useful down the road to make a selection of the material. So for a metal to plastically deform, dislocation must move. That's the basic principle. So strength and hardness is related to the mobility of the dislocation. If you reduce the mobility, metal becomes stronger or hardens. Greater force necessary to cause dislocation to move, that becomes why it becomes hardened. And if you increase the dislocation mobility, metal becomes weaker. And there are different ways you can increase the strength of the material by reducing the grain size, by solid solution strengthening, precipitation hardening, and strain hardening. These are the different ways, and I'm not going to go into details of those. Now moving forward to diffusion in solids, which is the phenomena of materials transport by atomic diffusion. And this is a basic formulation. And what it tells us that the diffusion coefficient, which is D, increase with increasing temperature. And the D dependency is given here. And if you look some of the results here, you have for the hydrogen, and this is for the deuterium, this is 1 over T, and this is a diffusion coefficient. So just giving you a rough idea where the diffusion will be faster and slower. If the structure is open structure, it will be faster. Materials with secondary bonding, smaller diffusion items, low density, these makes diffusion faster, and just opposite to that will make diffusion slower. Moving forward, this is a different ways by which metal can be fabricated. One is called forming operation, casting, and miscellaneous. And again, there are different categories of that, and I will touch base of some of them. So here is the different types of forming techniques. Here you have forging and swaging. This is the rolling, this is extrusion and drawing. And again, it has its own properties to deal with once you go through the forming. Now, one thing I will mention in the casting. So moving forward in casting, it's interesting that casting is normally done by molten metal filled in a mold. So metal is melted in furnace, perhaps allowing elements added, then cast into a mold. It is a common and inexpensive. It gives a good production of shapes. it's a weaker product. There is a lot of internal defects and good option for brittle material. So normally you adopt to materials when the material is brittle. But one thing is very interesting, that when you do the casting, you cannot do further processing. The casting material is itself in equilibrium, and it doesn't want to change the structure. If you want to change the structure, then you have to do some forming, like we discussed before. And then talking about the miscellaneous part of it, which is powder metallurgy and welding. So welding is very close to the structure which you get it in a casting. And powder metallurgy, again, is a fairly large subject, and I'm not going to go into details of that. And some of the aspects of powder metallurgy has been dealt in our US patent, which is just issued last month. So here is some of the characteristics or examples of a structure, property, and processing. So here you have some sort of I gave an example of a steel. So if you just cool the steel at a different rate, you are going to end up with a different types of structure, and you can see the hardness also keeps on increasing. So here is some of the properties by having adding some impurity in that. So if you look at that, this is the pure copper. This is the resistivity we are talking about. And so this is again, we are talking about thermal conductivity. So here in this first graph, you can see that with the addition of nickel, the resistivity of the copper increases. Here the composition of zinc, if you do that, thermal conductivity goes down. So these are then here you have the magnetic field so this is the iron. When you add some silicon, you can see the changes in the magnetic field. If you look at some of the optical properties, this is all of them are aluminum oxide, but it has become transparent, translucent, and opaque, and it depends on the material structure. So if you change the material structure, you can go from transparent, translucent, and opaque. Now, something about the grain boundaries. Again, this is a two-dimensional defect, and you can see that the orientation of the items here changes. So, and that creates a grain boundary. So these are the grain boundary here, and you can see if you make it perpendicular on the both orientation. So this is one perpendicular here, there is here, and this is what we call it grain boundary angle, and this is another one. So this is a low angle grain boundary, and this is a high angle grain boundary. And again, depending on the low angle and high angle, the characteristic changes. And you can see an example of the molten metal being poured into the mold, and once it is cooled to the solid, then you can see the different type of structure into that, and that happens because of the different cooling rate. And this is the polycrystalline material, which is isotropic. This is also polycrystalline, but it is anisotropic. But each grain is a single crystal, and I will talk something more about that. So isotropic and anisotropic means the properties of the material will change along the direction of the material. So this will be more or less isotropic, no change by pulling the material or doing anything along any direction. Here, there will be changes. So again, here is the example of single crystal, and here is the example of a polycrystal. Now this is what we are talking about. If you do the rolling, then you can have this material as elongated, and this direction will have a different properties compared to if you pull the material in the other direction. So nanocrystalline, I think it has become very important, and partly because it gives you option to have a large surface area. So normally when we call it nanocrystalline material, we talk about 100 nanometer, or 1 nanometer is 10 to the minus 9 meter. So if it is less than 100 nanometer, we call it nanocrystalline material, and grain size are typically considered ultra-fine grains. Now, the grain size of nanocrystalline sample can be estimated by X-ray diffraction. The crystalline size can be measured directly using transmission electron microscopy. And if you compare those to nanocrystalline, it refers to the structure, a small piece of condensed matter, not necessarily individualized, and nanoparticles only refers to the size of a small individual solid. So sometimes people make a problem in differentiating nanocrystal and nanoparticles. And here is something very interesting. As the size of the crystal goes down, the surface area increases, as I mentioned before, and it is given in the figure here. It is important to note that where surface plays an important role by reducing important input materials diffusion lengths. So the diffusion length gets reduced, and so the material can be loaded faster. So the left one is a 3 ways in which the cube of age d can be cut into layers, rods, and particles. And this picture here shows the total surface area A of the separated pieces as a function of number of cuts C normalized to d squared. And this is just a equation here, and this is a courtesy of Professor Nagel. Moving forward, this is another important topic, and this is hydrogen storage materials. And I'm not going to go into details of all those because it is very much involved. But this is the operational temperature and ability to store hydrogen given as weight %. Now, how much the work will prove to be relevant to LENR remains to be determined. Something important aspect of it, Pons and Flashman choose the experiment with palladium only because it has large amount of hydrogen isotopes, both protium and deuterium. Now, the lower cost of titanium and its ability to absorb hydrogen isotopes motivated immediate work after the announcement. And so is the case with the nickel also. So I will touch base with palladium some more and nickel. So here is the different mechanism which one has to be familiar with that, this of hydrating. So absorption of hydrogen gas on surface of metals and dissociation of the hydrogen molecules into absorbed items. So when you have a gas, when it absorbs, then you have a atomic. So diffusion of hydrogen and absorbed atoms into the bulk of the metals to form solid solution of hydrogen. If it is more, then becomes a hydride. So diffusion of hydrogen through the hydride layers to react with the underlying metal. So these are the different mechanisms for hydriding. Moving forward, this is the phase diagram of palladium hydrogen. And here you can see that this is the alpha phase here. This is a mixture of alpha and beta. This is beta phase. And alpha is the solution of hydrogen into the metal, and beta is the hydride. And if you look at some of the resistance, which normally we measure it in experiments, and this is a hydrogen going into the metal, palladium, and this is the deuterium going on. You can see the resistivity at this point, you have an inflection. So this will be helpful when we do this experimentation and make the measurement for the resistivity or resistance. Now moving forward about the nickel, because nickel has become very important because a lot of positive results has come out. So nickel, one thing here, that nickel is endothermic. When hydrogen goes into that, is endothermic, and as solubility increases with temperature. And just give you some idea about the nickel here. So here you can see that the solubility is very, very small. So main thing I wanted to mention here the nickel hydride dissociates spontaneously at room temperature under normal hydrogen pressure. And the room temperature solubility is very low. So that's the main message I wanted to give here. So moving forward, if you look at the other challenges which we have, so I'm going to talk now materials issues. So there are a lot of things here. The materials, as we mentioned, palladium, nickel, and we mentioned some of those things. A role of impurities, then allowing elements, grain size, I discussed, dislocation, I mentioned texture also, I mentioned powder metallurgy part of it, and we'll touch base with other issues. But let me touch base with allowing elements, which is very important. And what we did after the announcement, we started looking into different types of material, including palladium. So we looked at high purity palladium, commercial purity palladium, palladium silver alloys, because there was some potential thought about that, and then palladium boron, palladium cerium, and other alloys. But I will concentrate more on palladium boron alloys because that's where we got positive results. So let's talk about the phase diagram. So phase diagram, here is the palladium cerium phase diagram. Here is the palladium boron phase diagram. And here is the palladium silver phase diagram. So just to be familiar with that, this is the atomic percent on the x-axis, and this is the temperature here. So one thing here in the palladium boron alloy is we get a miscibility gap. And what I mean is that if we put the boron into palladium, in this region, the palladium breaks up, or palladium dissociates into two different phases, and I will discuss some more about that. And I will discuss more, as I mentioned, about palladium boron, because this is the alloy which gave positive results with the experiment done by Miles Miles at China Lake and in Japan also. And I will limit my addition of palladium in this region. So if you look at, so I just give you an idea how we made the palladium boron alloys. So we took a sponge of high purity 5,9 palladium and then high purity boron. Then used the arc melter with water cooled copper hearth. Then we took 3 boron, attempted to have a 0.75, 0.5, and 0.25 weight % of boron. After the making it, we annealed it, and there was average grain size is that one. The impurity level found out is this much here about platinum and copper and tungsten. And I will give you the details of the analysis also. The shape which came out from the melter was a irregular shape. So we rolled to the size, and then I will show you the microstructure on that. And we have 2 patterns on this process. So this is the glow discharge mass spectroscopy analysis, and we have taken Johnson-Matthey different purity content, and then you have got some NAWC Johnson-Matthey also, and then Goodfellow. So there's different types of palladium we got. And one thing interesting to see that there's some level of boron here and some level of silver here. So we thought that maybe boron and silver and some other elements might be helpful to have the positive reaction in LENR experiment. This just gives you some idea of the processing of the material. So after this is the arc melter here. This is we do swage it, and these are the different what do you call it, mold there. And if you look at that, these are the arc melting and casting mold here. So once we take it out, it is an irregular shape. And then finally, we end up with this type of shape here. And we send them samples for test at different places. So moving forward, so if you look at, this is a palladium rod only. And I've just wanted to give you an idea how the grains or the structure changes. Here, this material came out of the earth. And this one is material annealed at 650 degrees centigrade for 2 hours. And you can see the grain size. The grain size here is around 44 micrometer. When you anneal it at higher temperature, the grain size increases. And here is roughly 600 micrometer. And again, this material will be harder compared to this one here. And I mentioned before that grain size effect will be there on the material. Moving forward to the, this is a palladium boron. Now this is a edge swaged, means after melting we swaged it, and this is as swaged material. This is again annealed at 650 degrees centigrade for 2 hours, and grain size roughly 95. When you do it, this material is 0.75 boron. This is a 0.5 boron, and this is a 0.25 boron. And again, here is a 95, 100, and is a 125 micron size. And this is some TM, and again, there's a lot of work has been done on that, but I'm just showing one micrograph, transmission electron micrograph for 0.62 weight percent. I must mention here that we aim to make it 0.75 weight percent, but we ended up with 0.62 actual boron content in the alloy. So it may be hard to see, but the small dots are one phase, and then you have the matrix phase. And so the dots are roughly around 1 to 10 nanometer. And this one is a selected area diffraction pattern of the same material and area as in the overall image. So here is there some X-ray work. This is a 0.25 boron content. This is the pure palladium, and here is the 0.5, and here is the 0.75. So this gives you an indication that we have two phases, and here is the indication here. You can see this. This is the matrix lattice parameter. We are talking about weight percent of boron on the x-axis, and this is the other phase which is coming on. So as you increase the boron content, the other phase, which is a smaller phase, the lattice parameter increases, and this is the matrix one here. And we need some silver, different types of alloys. So let me show you about the silver, palladium silver one. So this is the palladium silver lattice parameter. So if you increase the amount of silver, lattice parameter increases, which is consistent with what we showed before. And this is just to give you an idea about what happens when you do some annealing. So this is the annealing at, this is grain size here, this is time in minute here. And so these are the, here for the pure palladium. And this is 950 here, and this one here 950. And this is a 650 here. And this is for palladium silver. And you can see that the higher temperature will give you higher and larger grain size, and this is for 650 here. And again, just to relate to this one here, you can see here that the micro hardness changes as we change the grain size. So grain size also plays an important role in two ways. Materials mechanical property changes, and another one is that diffusion will be faster in a smaller grain size compared to the larger grain size. So looking at further, just to show you some of the calorimetry work which is done, and then progress and the summary. So here is the calorimetry work, and you can see here, this is the NRL palladium. We didn't get any excess heat. This is the palladium cerium boron alloys, which we prepared it. And also we didn't get, and again, this is a time here, and this is excess heat here. This one here is a palladium silver. Again, we didn't get excess heat. So all these materials, we try to find out the calorimetry and find out whether the excess heat comes or not. But we didn't find any in any of these alloys or palladium. And this is for palladium boron, and I'm just giving it for 0.75. And again, this was the aimed at 0.75, but we ended up with 0.62 boron content. And you can see the excess heat here. And here is for 0.25 boron. And again, you can see the excess heat there. So, and we sent some sample to Dr. Storm also, and he also got positive results. So just to wrap up what we have seen so far, the 3 different composition of palladium boron samples produce excess power in channel lake. Studies, all these alloys have 2 FCC phase, which I mentioned before, with a different lattice parameter. And excess power appears early in the experiment with the palladium boron alloys. That's another good part. And then palladium silver, palladium boron cerium failed to produce any excess heat. Ada Storm reported excess power in 0.25 palladium boron alloys using closed system. And recently, Professor Zhang also found out that there is an excess report in palladium boron alloy, which is supplied by male miles. Important to understand the relationship between properties, structure, and processing. Materials can be single crystal and polycrystal, but sometimes it is a preference is to have a single crystal, because then you can pinpoint some of the effects more easily. So material can be single crystal, polycrystal, as I mentioned before. Materials properties varies with single crystal orientation, which is what we call it isotropic. And in polycrystal, which is randomly oriented grain, properties are not, it is isotropic, as I mentioned before. Nanocrystalline materials offers advantages because of the surface area. And phase diagram are a useful tool to determine the number types of phases, weight % of each phases, and composition of each phases for a given temperature and composition of the system. And we use normally X-ray diffraction to find the crystal structure and interplanar spacing. With that, let me wrap up.